Welcome to Statistical Computing with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we're going to look at a range of plots that you probably have never seen before and may never use, but it is a fun way of looking at data in different ways. So I'm going to scroll down to More Plots. So that's this lecture right here. So I'll switch over to the lecture. This, rather than being in slide format, this is in book format. And we'll look at these types of plots: the tree plot, parallel sets, Sankey, steam graphs. A fun plot when data either fits your model or does not. I show a lot of chorograms or parallelograms for correlation plots, not necessarily because they're important, just because there's lots of implementations of them. A bee swarm plot, back-to-back histogram, and we'll talk about N graphs. And we'll talk about each of them and their merits and dismerits, I suppose. So I'll page down. So more plots in R. So there's lots of packages used in this chapter, and this bit of code here at the top will go ahead and install each of these packages, as well as their dependencies. So the first is a tree map plot, and this is used for hierarchical data. There is a library called tree map, and one of the default database or data frames in there is the gross national income per capita in dollars per country in 2010. So, the globe has a natural hierarchical structure and continents and so on. So here is the data frame, which has 208 observations and these 5 variables. It has the country name, we have which continent we're in, we have the population of that country, we have the GNI, and we have the ISO 3, some categorical variable, I suppose. So here is the tree map plot that's being used, and it's being indexed first by continent and then by ISO 3. The size of the squares, we need to see the plot in order to talk about it. Alright, so here we have the tree map plot. Notice Asia is a big label in the center of this big square. Okay, all of that is Asia. We have China here and India here. Now the size of the squares, now if we scroll back up and look at that, the size of it is based on the population. So the populations of China and India are comparable, and they're both by far the largest in the world. The color is the GNI value. Okay. So if we scroll down at the bottom of the plot, there is a color bar, which is GNI, and it goes from 0, which is this very light color, to dark, which is the high number. In the upper right-hand corner, we have Europe, and so we've got Russia here, we've got Great Britain, we've got Italy, we have Spain, and then we have North America, we have USA and Mexico next to each other, and so on. So when you have data that are hierarchical, the tree map is one strategy for this. And there are several examples of this, which I've looked at many times with my classes. And so if we open up one of these tabs, this is a tree map plot of Obama's 2011 budget for the United States. Okay, this was the proposal. This isn't necessarily what was spent, but we have here a total of $3.69 trillion proposed, and we have national defense in this upper left-hand corner, Social Security. So national defense and Social Security about the same amount. We have Medicare. We also, next to that, we have healthcare, which I think of as being something similar to Medicare, but or at least a subset of that, but it's not in this case. We have net interest. I think this is probably on the loans that we owe to other countries. Income security, and then things start getting small. For example, education, veterans benefits, and so on. If we click here on education, this plot has this nice dynamic thing where it will zoom. So we've got, and as you hover, we have words here. This is probably really hard to see on the video, but we have special education in this square. And it just shrinks and shrinks and shrinks. What's one of the smallest ones here? Elementary, secondary, and vocational education. Okay, a few $1,000,000 for that. We can zoom back out. So that is a tree plot. The following year, oh, that's too bad. That worked until today, I guess. Okay. Very good. So that's enough about the tree plot. All right. Let's talk about the parallel sets plot. So when you have categorical data and you want to visualize this over several categories, this is one way to do it. This is survival status of the Titanic. Up at the top, we have a first category, whether they survived, yes or no. And the length of the horizontal line indicates what proportion that is. You know, about a third, maybe a little bit less than a third, survived. Then we have a second category, sex, whether you're male or female. And one thing that really stands out to me is if you are a male, predominantly you are not a survivor. Whereas maybe about only 20% or 25% of the males survived. Whereas for females, about 2/3 survived. Furthermore, we have the class. So first class, second class, third class, and crew. And there certainly was, as there always is, a positive relationship between survival and class. So here about, a little bit more than half, maybe 60% of first class survived, about half of second class survived, about a quarter of third class survived, and maybe about 20% or so of the crew survived. So this is one way you can reorder. This plot definitely starts at the top, and as you come down, it breaks into categories further and further. I don't think this is necessarily a great display, but it does help tell a story, and we were able to get that bit of a story just from looking at this plot. There is, above that plot, the code to make the function for that parallel set plot. And it was run with this command. MYT is my Titanic dataset, and then the parallel set plots specifies the categories: survived, sex, class, and then you assign some aesthetics such as frequency, color, and alpha is the transparency, so that's why you see a blend of colors here. All right, Sankey plots are used for categorical data when so we've seen an example of this before when we saw Napoleon's march on Moscow. There was a bar that decreasingly got smaller and smaller as people died in the army. Okay? In this case, we're looking at people who enter a study. So there were people who were referred. 96% were referrals. There was 4% up here are transfers. I recognize that is very small for you. Okay? And the words here, the relative size of the words is the relative size of the category. So we got lots of referrals, 144. We have 6 transfers. They all enter the study. This hyphen indicates when they stopped entering. And then people leave for different reasons. Okay? So you can think of this horizontal line as time, and 6 of them were unable to engage I'm not sure exactly what that means in this case. 47 were for consultation only, so that was about a third of them. And then there were lots of other reasons why they didn't participate. Finally, active in treatment, we get about 23% of them continue to go on and participate in this study. So it's one way of visualizing flows in and out. I think there are more beautiful ways of visualizing than this. This is not a great display. Text is over on top of text. These arrows go straight up and cause issues about these diagonal text. I think there's other ways to do this. All right, STEAM graphs. It's also stack density plots. These were introduced on New York Times box office revenue plot. I'm going to open up that link so we get a look at. Oh, New York Times took down all their best plots. All right, let's find another one if we can. Well, we'll see one in a second. Okay, here we go. So here are 15 density plots that are overlaid on top of each other. Okay, so for example, this red plot happens to be at the bottom, and then stacked on top of that is this lime green one, and at the very top is this cyan, this light blue. Okay, and so one thing that this displays very well is if your eye follows the top of the curve, you do see what the total is very well. The issue that this presents is because we are not measuring from a common axis, the vertical distance here, this pink, how high is that pink one relative to the pink down here? Okay, we get a very clear picture of what this red one is and what this orange one is because it's measured from the bottom, an axis that's horizontal. As soon as you modify that bottom axis, for example, this gold is on top of the orange, so its bottom axis keeps changing as well as the top axis. It's an impossible ask to have us interpret something like that. I'll just show you this one just as a demonstration. Okay, what shape or what's the distribution of the brown curve, or what's the distribution of the pink curve, or of this beige color? It turns out, and your eyes are going to play tricks on you, that if you don't stack them, these are all normal distributions with different locations but the same scale. But it is almost impossible to reveal that just by looking at the stacked distribution. So you lose information by stacking. You do gain the total. It is hard in this bottom plot to indicate what the total is if you were to add these curves together, and that's very clear in this upper plot. So you have to think about, in a visualization, what your goal is to communicate and do that well. If you're thinking of the total, then stacking is probably an okay idea, but you lose the individual components. So actually presenting two plots, as I've done here, together may be a nice solution to that. All right, this one's just for fun. What if you've got a model that you've got data and you fit a model to it, but there's no real relationship, right? So you can use this function called smile, and you can make a grumpy emotion, and rain and dark clouds will join your data points. But say you've got a nice relationship, and you want to fit a quadratic regression line as a rainbow. Then you've got a rainbow, you got smiles, things are good. I recommend not using this in your thesis and dissertation presentations, but it could be fun. All right, let's talk about correlations. So we have all created scatter plot matrices of data sets with many variables, okay? And we're often interested to know which variables are related to others. And one way we can assess that measurement or those relationships is by correlation. Are these points linearly correlated, linearly related, and by how much? The strength of the correlation. So that's this section here. So this scatter plot right here, this upper triangle, is very small. Okay. And looks like this is some automobile information. We've got miles per gallon. We have engine displacement, number of cylinders, horsepower, and so on. Number of gears the car has. And it looks like there's some negative relationships. For example, the miles per gallon and weight has a negative relationship here. All right. So how do you quickly let your eye understand a scatterplot matrix? It can be pretty challenging. So the value of these plots I'm about to show you has to do with very quick interpretation of correlation matrices or scatter plots. So you can take this scatter plot matrix and convert that to correlations. So on the left-hand side, we've got colors, and each color indicates a value for correlation. Notice also that the variables maybe have been pre-ordered here, since we have all these negatively correlated variables together, and we have two sections of positively correlated variables in the top left and in the bottom right. So this is using a few ways to display the strength of the correlation. We have color, red or blue, which indicates positive, and I think red is probably negative and blue is positive. We have in the bottom left just the color, and we also have a direction, these lines. So red, we have this decreasing line for negative, and for blue we have positive. In the upper, we've got those same colors, except we have a pie chart, which indicates a proportion of 1 for the strength of the correlation. So for example, this pie chart in the top here, that's halfway, that's a correlation of 0.5. And it's red, so it's negative. All right, let's look at a few others. In this lower left triangle on the right plot is showing ellipses and a sort of a smoothed regression line through the data to indicate some degree of linearity or not. So that is coming from a package called CoreGram and the CoreGram function. And here I've created two plots using different options, and I'll let you investigate those options. The next is some more examples of this. For example, you can remove one of the triangles since there's a redundancy there. You can also change the color palette. All right. So here is a base graphics version of a correlation scatterplot matrix with regression, with a smoothed trend line through the data to indicate the amount. And in the upper triangle, we have correlation numbers, and the size indicates the strength of that correlation. And we also have some stars, which I believe indicate significance, testing the hypothesis whether it's different from 0. So we can look at some of the code that created that in this function here that was defined for a panel for the correlation. And if you look through here, here are cut points for a p-value for testing whether the correlation equals 0. And so these are the stars that are being plotted. And we also have the text where the size of it, CEX, is a size parameter. So the size is based on the strength of the correlation. And same thing with those significant stars. Those stars are based on, are just all the same size? Okay, not sure. So another way to do scatterplot matrices is the ggalley, which requires ggplot. And there we go. Here's the default version of that type of scatterplot matrix. I actually really like this sort of display. I like the gray background. I like the grid lines. I like the marginal density plots, smooth density curves along the diagonal axis. And we still have those correlations labeled on the upper diagonal. All right. And there's a few more. Here's one where we've got color and size for correlation. Here's the ellipse package will give you ellipses and colors. So notice that these numbers are dual coded. What do I mean by dual coded? I mean that correlation has been encoded using two different aesthetics. We have here a positive correlation between cylinders, number of cylinders, and weight, and it's colored in blue. And here we have a stronger correlation between displacement and weight. So the color blue indicates the strength of the correlation. We also have the ellipse shape, which is coding the same information. It's generally not great practice to code things with more than one aesthetic, or geometric object, but sometimes it can work pretty well. And in this case, I think it works just fine. Though there is a secondary issue about area. The stronger the correlation, the smaller it is. So we've got big circles here when there's correlation is roughly 0, and then we have small ellipses here when the correlation is very strong. So our eye may be drawn more easily to these big circles because of the size. All right, and here's basically that done in a very clean looking scatterplot way. We've got the numbers and we have the, I guess it's triple coded actually, because the ellipse, it cannot be separated from the area that it also encodes. That's also happening. All right, let's talk about the B-swarm plot. This is like a dot plot, but it's organized in a symmetric way, similar to the way a violin plot is organized. So in the left-hand side, we have the B-swarm plot in basic graphics, and in the right-hand side, we have this in ggplot. So we've got a box plot underneath, and you can see every individual point is plotted. So it would actually be possible to retrieve the original values from this plot, whereas from the box plot, of course, alone, you certainly couldn't. And from a violin plot, which is a smoothed symmetric density histogram or density curve, you couldn't retrieve the original data either. And notice I have an additional coding over on the right of positive and negative, so I've got red and blue points here. Not a big deal. That happens in the left as well with the green and the blue or purple. All right, back-to-back histograms. I see this sometimes in order to compare distributions, and that's on the left. So I've just simulated some data, and we've got males and females, and we've got, again, we have dual coding here because we have a position. If you're on the right, you are a male. You don't need the blue. That's a secondary encoding. All this could be gray, for example, and females are red on the left. And the idea here is to look along this axis, the y-axis, and compare whether the reds and the blues are bigger or smaller than each other to see how they compare. Now I find this a challenging visual exercise because even though they are along a common horizontal axis, they're in opposite directions, and so I'm constantly having to work my eyes back and forth to compare. I think this puts a lot of stress on your viewer. On the right is an alternative where I've simply overlaid the two distributions on top of each other and allowed some transparency so you can see both curves. You can see where the red is above the blue, and you can see where the blue is above the red. And everywhere else, they overlap. these two distributions are actually the same distribution, and any difference is just simply due to sampling variability. I think you get the same story from the left plot as you do from the right. It's just makes your brain work harder when you're on the left. Networks, or graphs, are very challenging to display. I have a lot of code here to create two separate graphs. I'm going to zoom in just a little bit more. On the left is a fairly traditional display of a graph. Zoom out just a little bit. Where we have, this is a directed graph, so we have arrows. We have line segments and arrowheads. So for example, from this dot, it's directed from here over to the left to this dot. We have some nodes that are not connected, and we have some pairs of nodes that are connected in both directions. So there's an arrowhead on both ends of that line segment. An alternative way to display that, and one that has a bit of research to say that this is a little bit easier to view, though I find almost all network graphs fairly challenging to view. You are, after all, taking in a lot of information in a network. So here's that same first line segment. We're going from this point toward the left to this point. So that decrease in size indicates that we're going from the fat to the skinny end of that line. Bidirectional, this one that we looked at before, has thickness on both ends, though the person who designed this made the choice to have one end be dark and one end be light with dark outlines. I find that asymmetric visualization not very helpful, because there's an asymmetry. It appears that there's some meaning to that, and perhaps that there's something about direction there, but that's not the case. I do think the plot on the right is cooler looking, but I'm not sure that I'm getting more information from the one on the right versus the one on the left. And both are very hard to read because we have many nodes. Yeah, maybe I'll just end by saying graphs are a pain. And there are lots of layouts for this, ways of organizing nodes, and very few of them do a really great job. But you do what you can to make whatever you're visualizing as clear as possible. All right, so that's been some fun graphs.